Hello everyone and welcome to my database management lesson over relational model and database design using normalization. So there's a lot of information rolled up into this one lesson as we talk about database design and the need for normalization. We will briefly talk about denormalization, which is just the opposite, and I've hardly ever seen it used, so I won't spend a lot of time on it, but it is just the opposite of normalization. Now, typically when we are designing databases, sometimes you'll see that you're either starting from scratch or the design might arise from existing data sources, like information that's typically been captured on spreadsheets or that was contained in text files or even other database extracts. So the relational model is very important, and the act of taking our data and normalizing that is extremely useful. Normalization is just a process of transforming our relations with modification problems into more usable data. And we can use normalization principles to guide the overall design of the database from when you're using existing data. You will be surprised that even a single table can have much complexity in it. And when we see that there's a lot of complexity in a table, that's usually a good sign that there is a need for normalization here, so we can separate that into multiple tables or multiple relations, or more specifically, multiple entities. So let's take a look here. Well, we've got some information here in front of us. Now, let's just ask ourselves a question. Should we store these two tables, order item and SKU data, in as they are, or should we combine them into one table in our database? These are those flat files that we've been given. The information you can see in order item, we have several different attributes or columns, and we have order item, SKU, quantity, price, and extend price. And we have several rows of data, and we'll come across different terms that we will use interchangeably. So you might hear me say that order item is a table, or you might hear me say it's a relation, or some people might even call order item a file, its own individual file. And then when I talked about the columns there, such as order number and SKU, sometimes we refer to that as attribute, or some people even call it a field. And this is because of using different databases. And then lastly, you heard me call the rows, like row 1 has item 1000, of SKU of 201000, quantity of 1. That's typically called a row. You might even hear this more specifically called a record. And if you've ever used Microsoft Access, you might have heard that term record as well. And then some people, and this is very few, might even call it a tuple. Yeah, I probably won't use that term very often at all. But those are some of the general terms. We'll get into those more later. But as you can see, we have these two tables here, order item and SKU data. Now if we combine those, you can see how that might look down here at the bottom. We've just brought all of those columns or attributes or fields into one table or one relation, and we are going to have all the data right there as they relate to one another. So it's up to you. If we were combine this into one table, you can see where we have some redundancy, and there's some issues here with that. So when we normalize data, we typically break that into smaller tables so that we don't have as many issues. When we make the decision on how to design our tables, we are going to obtain certain advantages at the expense of certain costs. So let's take a look how we can weigh out those advantages and those costs. Now we use the relational model, and I might have just skipped over that. This is introduced way back in the 70s by E.F. Codd, and it was a design that used mathematical information from relational algebra, and that's how we get the term relational from this. So for our database models, this is pretty much the standard we use still today for the design of our commercial database management systems, such as Access or Microsoft SQL Server. But all the information from this paper is what we use to design our database management systems. So if you can remember E.F. Codd, it will probably help a lot when you're trying to understand that this wasn't designed by IT professionals. This was a engineer who used mathematics to say, this is how we should model our data. There's a lot of terms that come into play here, and you can see I've got a list of them here. And we will take a look at all of these and kind of go over them real quick. Now for the term relation here, this is, and I used this term a little bit ago, this is a table-like structure, a two-dimensional table of rows and columns where the rows store the data about an entity and the columns store the data about the attributes of that entity. Each column in this relationship, or in this relation, is going to have a unique name, and all the values in a column are for the same attribute. So as we go down a column, it's going to have a unique name at the top, and all the values in there for that column are all going to have the same attribute. Now the cells in our table can only hold a single value. We do not want multi-valued fields here. And the order of the rows really doesn't matter. Neither does the order of the columns. The data in each row as a whole must be unique, so we do not have redundancy of data. We have functional dependency, which is just a relationship between attributes in a relation where the value or values of one or more attributes determines the value or values of another attribute or set of attributes. For example, and functional dependency is a little tricky, but once you do a few, you'll have no problems. But functional dependency, like A is going to be the determinant of B. And you can see where I'm using a couple terms here. They're probably pretty confusing, which is why I'm going to wait and talk a little bit about that here in a few minutes. We have candidate keys, which are just an attribute or even a set of attributes that uniquely determine the values of all other attributes for a row or a relation. Now a composite key is a key that contains two or more attributes, and you'll hear the word composite used quite a bit in terms of database management. Primary keys, you've probably already used to this if you've ever worked with a database management system like Access. A primary key is just a candidate key selected as the official key of an entity or of a relationship. A surrogate key is created. This is a column of artificial data added to a relation to serve as a primary key. This is where we have an entity and we don't really have anything that's completely unique. Well, we might create a surrogate key that, let's say we will call it employee ID, or let's say we have students, but we want to give them, they don't really have an official key that separates them individually. We're going to create a surrogate key, we'll call it student ID, that now that has a number associated to a student's name or a piece of information associated to a student that is completely unique to them. We have foreign keys. This is like a primary key. It's an attribute that is a primary key in one table, but then it's placed in a secondary table to form a relationship between the tables by the first table storing those values. The term foreign key is going to refer to the attribute or set of attributes in the second table, not the first table. So in another table, it may be a primary key. In the secondary table, even though it's the same information as the first table, we call that a foreign key. Referential integrity constraint. This is a value constraint of a foreign key, as I just mentioned, that states that no value can be placed in the foreign key unless it already exists as a primary key value in the linked table. We have normal form. This is a category and a set of categories called normal forms used to describe relations according to the type of anomalies that can occur in those relations. We'll talk more about normality later on. And multi-value dependency. This is an anomaly that occurs in a relation where a determinant is matched to a set of values rather than just a single value. And this is, a little bit confusing as well at first, but as you practice it, you'll get more used to it. Now if we take a look here, I said an entity earlier. This is something that is identifiable that we want to talk about. So if we are going to talk about our customers, and we have customer names, we have customer addresses, customer phone numbers, the overall entity, the identifiable thing that's in common that we want to track is just generally customers. If we want to talk about the sales of our RAM, the sales of our hard drives, the sales of our PCs, generally this is what we're going to say is one general category or an entity is just sales. So that's how we define an entity. And the Relational Database Management System, or DBMS products, store data about these entities in relations, how they relate to each other, and that's a special type of table. We can have a table that does not have a relationship, but the ones that do have relationships, we call those relations, and that's where we get the term Relational Database Management System. So a relation, as I mentioned earlier, is just a two-dimensional table that has some of these characteristics. The rows contain data about a single entity. The columns contain data about the attributes of those entities. All entities in a column, that up and down area, are of the same kind. So if we have an attribute in an entity, the attribute is, let's say, eye color. Then we could have like blue, hazel, green, but we would not put like a phone number in that same column because that is a completely different kind of attribute. So that should not go in the same attribute column as eye color. Cells of a table hold a single value. Like I said, no multi-valued cells. The order of the columns is unimportant. We don't care about the order of the rows. We can always manipulate those. And the big one here, no two rows may be identical. We want to make sure that we reduce redundancy in database management, and we definitely do not want to have any identical records or rows of data. Now, I mentioned about how we want the values in a column to be of the same type of data. It's what we call domain integrity constraint. The requirement that all of the values in a column or an attribute are of the same kind is known as domain integrity constraint. The term domain means a grouping of data that meets a specific type or specific data type. So you can see, like in first name, if we have a column of data or an attribute that's called first name, we want those to be all in that column to be the same type of data. We want it to be Albert, Bruce, actual first names. We don't want to put some random values such as a phone number in there. And then columns in different relations may have the same name or the same attribute, but if they are not exactly the same, we want to make sure that we name those just a little bit different. If we are doing sales data for we have a manager, and that manager's name is Bob, and then we have a customer whose name is Bob. We don't want first name to be the same attribute name in each of those. We might want to have the manager as manager first name or manager first. We just want to make sure that they're a little bit different. But if we are using a foreign key, we want to make sure that it's the same as it was in our primary table that came from. Here's some of that alternate terminology I talked about earlier, how you'll hear these terms used synonymously, where someone might say the word table, and it's the same thing as calling it a relation. Or we might have a column, and just like I've been doing, calling that an attribute. Or a row of information, you might hear it called a record or a tuple, and you probably won't hear the word tuple outside of academia. Now, when we talked about COD earlier, and that paper that COD did, you can see there are a couple key elements here. In a relation, the rows relation must be unique. There must be something there that designates them as unique. Now, there is no requirement for a designated primary key per COD, but in the database world, honestly, you want to have a primary key in every entity or every table. So it's just the best practice. So that is up to you as to when you determine that, but it's hard to create those relationships and have normalization if you don't have a primary key. So let's make sure that we are always determining and assigning a primary key. Functional dependency, this occurs when the value of one set of your attributes determines the value of a second attribute. And I said this could be a little confusing at first, but just think about that functional. It's functionally dependent upon something else. So occurs when the value of one attribute determines the value of a second attribute. So student ID is the determinant of student name, and student ID is the determinant of the dorm name, the dorm room, and a fee. So the attribute on our left side of this functional dependency statement here, it's called the determinant. And functional dependencies may be based on equations, but not every functional dependency is an equation. Don't even think of it as an equation, just think of it as how they make sense as to, is this information dependent on the other? So let's take a little bit further look into that. You can see, and I've tried to make this look a little bit cleaner here. The information on the left determines the information on the right. So the object caller determines the weight. So you can see that if we know this information, we know that if it's a ball, it's red and it weighs 5 ounces. If it's a cube, it could either be blue or it could be yellow, and it could either weigh 5 ounces or it could weigh 7 ounces. But if we know the color, we know the weight, because we don't have anything that's not similar there. If we pick out red, we know it's 5. We know that it's not 7 ounces. If we pick out a yellow object, we know that it's 7 ounces. It's not 5 or anything else. As you can see here, weight is functionally dependent on the object caller. Object caller determines shape, and object caller is the determinant between weight and shape. So it's just a lot of practice to get used to this. A composite determinant is, and as I said, you will see the word composite used lots in database. A composite determinant is just a determinant of a functionally dependency that consists of more than one attribute. So student name and class name are the determinant for grade. Grade is functionally dependent on the student name and class name. Here's some dependency rules. If A is the determinant of B and C, then A is determinant of B and A is determinant of C. And we get that. That's called the decomposition rule. That's where we're taking that and breaking it down or decomposing it into individual components. If A is the determinant of B and A is the determinant of C, then A could also be said that it's the determinant of B and C, written as B comma C. However, if A and B are the determinant of C, then neither A or B can determine C individually. They must be together. They must be a composite. And up above, when you talk about union rules, hopefully that will make sense to you, that in that functional dependency rule of if A determines B and A determines C, then we have a union of information between B and C based on A is the determinant. I know it's a lot of terms, but hopefully just through practice you will get used to it. Alright, we used the term key a couple times. This is a combination of one or more columns that is used to identify rows in relationship. Here's another instance where we use composite key, and that's where we just have 2 or more columns combined together to make a single key. We talked about primary keys, foreign keys. A composite key just consists of 2 or more columns to create that composite key. This is where if we don't have a completely unique identifier in our entity, then we can combine 2 so that the combination of those 2 attributes make that row unique to any other row in our table. Alright, so a candidate key is a key that determines all of the other columns in a relation. Primary key, as we talked about earlier, is a candidate key selected as the primary means of identifying rows uniquely in a relationship. And there's only one there's only one primary key per relation, and that may be a composite key, a combination of multiple attributes. Ideally, we want our primary key to be very short, typically numeric, and it's never going to change, so that it is completely unique, so that every record in our relation is completely unique, and we do not have any chance for redundancy or any type of errors from our primary keys. We have an entity integrity constraint or rule, and the requirement that in order to function properly, the primary key must have unique data values for every row in the table. This is what we want when we are creating a good table or a good entity, is that we have the entity integrity constraint so that we do not have any other rows that duplicate each other. A surrogate key, as I mentioned earlier, is just an artificial column added to a relation to serve as a primary key so that it can be unique. Typically, you will see that your database management system can supply this. It will automatically create a number for each new row. And we do not use this, since it is an artificial piece of data. We don't use this in any type of forms or reports to reference that surrogate key. If we take a look at this here, in our rental property table or entity here, we have these columns listed here, or these attributes: street, city, state provenance, zip, postal code, country, and rental rate. We want to have a surrogate key, so we're going to just create one, because nothing here is going to be unique unless we create one, this surrogate key, so that it will be completely unique. It will keep our rows completely unique in our entity. So we just create one called property ID. So that property ID surrogate key, it's not really meaningful to anything. It's not data that's really valuable, but it's going to create that uniqueness of the rows that we need. Now, foreign key is a primary key of one relation that is placed in another relation to form a link between the relations. So we have a attribute in one table that's a primary key. We have another table, and we want to use that key again. So we're going to have that same attribute, same data in this second table. Well, it is a foreign key in this new table, because it is a primary key in another table. But now, because we're using that data in both tables, we have a relationship between the two tables. Once again, this can either be single column or single attribute, or it can be multiples, creating a composite key. When we want to enforce referential integrity, this constraint, it's a statement that limits the values of the foreign key to those already existing as a primary key value in the other part of the relation. Let's talk about normality. You can see that here's where we're going to start our next lesson. So I'll do a follow-up video to start with our discussion on normalization.